Last time we saw that molecules form conformational isomers when they rotate and fold themselves into different shapes, and those different shapes can have different functions and properties. This time we're going to talk about another type of isomerism where two molecules can have all the same atoms bonded to all the same atoms, and yet there's no way to rotate each other to make them exactly the same. For the simplest version of this, let's take a methane and start replacing hydrogens with different halides: fluorine, chlorine, and bromine. When we draw it in 2 dimensions, it doesn't look like it matters which halide we put where. But let's look again in 3D. If I exchange the placement of 2 terminal atoms, let's say the hydrogen and the bromine, both of these molecules are still perfectly legitimate bromo-chloro-fluoro-methane molecules. But they're still not the same molecule. No matter how I spin one, I will never get it to match the other perfectly. These are called stereoisomers. Stereoisomerism is possible when a carbon has 4 different constituents. That carbon is called a stereocenter, or a chiral center. You might also notice that these 2 molecules are mirror images of each other, just like your left and your right hand. These are called chiral molecules, from the Greek word for hand. Actually, we still label them R and S for rectus, right, and sinister for left. Now, there are a set of rules that help us decide which one is the R and which one is the S version of the molecule, and those you're going to learn in second year organic chemistry. Just like conformational isomers, small differences in the shape of stereoisomers can have huge impacts on their function. A fun example is carvone, an aromatic chiral molecule. R carvone smells like spearmint or wintergreen lifesavers and can be used as a mosquito repellent. S-carvone smells like caraway seed or rye bread and can be used to preserve potatoes in storage. More serious examples we find in pharmacology. Our DNA and RNA and many of our proteins are chiral molecules, and so chiral drugs can have wildly different interactions and outcomes. The most famous example of this is thalidomide, a chiral drug prescribed to pregnant women in the 1960s to help with morning sickness. The commercial drug was a racemic mixture, a mixture of both stereoisomers. While one isomer reduced morning sickness, the other was responsible for thousands of babies born with malformed arms and legs, and even more serious birth defects. Except, that is, for in the United States. Fortunately, the U.S. Food and Drug Administration had assigned the approvals process to Canadian chemist Frances Oldham Kelsey, who was not satisfied at the company's assurances of the drug's safety and efficacy. She was petitioned 6 times to approve the drug, and she rejected those petitions every single time. Her strong personal stance to ensure that the drug would work as advertised, without harm to mother or baby, protected thousands of potential victims and led Congress to pass legislation that made the scientific evidence that Dr. Kelsey had asked for mandatory before any new drug would be approved. It's worth noting that Dr. Kelsey was accepted into her PhD program at the University of Chicago by mistake. When her future supervisor there had received her letter of application and her transcripts from McGill, he had assumed that Francis was a man. Now, more than 20 countries, Canada included, had already approved thalidomide when it came across Dr. Kelsey's desk. Consider how many other tragedies were not prevented, and how many are still likely to occur due to arbitrary prejudices and harmful discrimination that she and others continue to face.